Welcome. Today we are discussing Module 6.2, Implementing a Basic Retriever Chain, Practical. Here is a quick look at where we are in our curriculum. Welcome back, developers. Today, we are shifting away from high-level theories to write actual production-grade code for a basic retriever chain. A retriever chain is the nervous system of any retrieval-augmented generation, or RAG, application. In this architecture diagram, you can see how a user's query flow splits. First, it fetches contextual vectors from a vector store, then it formats those vectors into a standard prompt template, and finally, it forwards that rich structure to an LLM. Please make sure to check the link in the description to download this complete architecture diagram and our reference scripts to run locally. Let's write the system step by step. First, we need to ingest our unstructured data. Here, I will implement a modern script utilizing ChromaDB and standard OpenAI embeddings. We define two document objects representing internal human resources and financial policies. I am using the text embedding 3 small model, which offers a great balance of performance and dimensional accuracy. We feed these items directly into our Chroma vector store, generating mathematical embeddings representing our policy documents in an instant. This will form the source pool for our retrievers. Let's run this code and check the initial logs. When we execute this script, you will see a clean terminal response indicating that the Chroma vector database has successfully indexed our documents. Behind the scenes, the OpenAI API is queried once for each text snippet, creating semantic embeddings that are loaded directly into the active RAM space for immediate access. There are no critical validation errors, and our system is now fully prepared to retrieve content. Now, we will define the actual retriever wrapper using our new vector database. I will configure the retriever to use standard similarity search and limit our response parameter, k, to exactly 1 document. This prevents overwhelming the LLM with unnecessary text. Next, we construct a chat prompt template. Note how we explicitly define placeholders for the context and user query. Remember to check the link in the description to download this prompt schema. Let's look at how the prompt is structured in code. Upon running our component pipeline script, the output shows successful setup confirmation. This validates that our retriever object, our customized system prompt structure, and our GPT-4o mini model have loaded properly with 0 library conflicts. This stage ensures our pipeline pieces are ready for seamless composition using LCEL. Let's stitch everything together using modern LCEL. I am going to define a variable called rag_chain. Observe the syntax. We use a dictionary helper containing runnable passthrow. When a user inputs a query, runnable passthrow passes that exact string directly to the retriever to gather our documents, and preserves it as the question key. Both of these outputs stream into our chat prompt template, feed into our LLM, and pass through str output parser to guarantee a clean text format. Let's see how simple this looks in Python code. Here are the live terminal output logs from running our query. As you can see, the retriever successfully matched our query about office setups with our custom finance policies document. It completely ignored the irrelevant HR text and generated a highly accurate, grounded response explaining that the remote stipend limit is exactly $500. This is the complete proof that our retriever chain is functioning flawlessly. When building retriever chains for production systems, you must consider critical configuration trade-offs. If you set your parameter k too high, you might overwhelm your LLM with raw data, which increases costs and risks hallucination. Conversely, if your k is too low, you risk omitting key information needed for complex answers. To mitigate this, consider implementing advanced retrieval configurations such as MMR, maximal marginal relevance, or introducing threshold filters to balance content diversity with query precision. In this session, we built and ran a basic retriever chain using LangChain, proving that we can dynamically feed custom context into our prompts. But what happens when our retrieved documents contain conflicting facts, or when the LLM makes up details that aren't in our text? This is where theoretical evaluation becomes essential. In our next lecture, Module 7.1, Synthesizing the Final Answer and Hallucinations, Theory, we will dive deep into how to build robust guardrails, analyze generation safety, and ensure your LLM never speaks out of turn. I will see you there.